Welcome everybody. My name is Jason. I am the virtual teaching assistant of Professor Sorrentino for this course. Let's start another episode of Process Fluid Dynamics. For getting deeper into the key aspects of the behavior of fluids and process machinery, we are still dealing with a chapter related to conservation principles. And now it corresponds to give some words about the Reynolds transport theorem, also known as the equation of variation. The Reynolds transport theorem was developed by Osborne Reynolds and published by the Royal Society of London in 1903. What is today known as the Reynolds transport theorem was named by him as the general equations of motion of any entity. Being entity supposed to be either mass, momentum or energy, let's identify that this concept relates the conservation principles formulated for constant mass or systems to this principles to be used for control volumes. To keep the formulation general, the variable B is introduced, that represent the entity being considered, to which the conservation principle is applied. A second definition is necessary, that is the corresponding intensive variable, beta, which is the derivative of B with respect to mass. Beta what B1 is B is the mass velocity if B is the linear momentum, and specific energy at B is energy. At time t, the initial mass, red dashed contour, and the control volume solid blue border coincide. But certain time later t plus delta t, the initial mass, black dashed contour, is moved. Some mass entered and some mass exited from the control volume. It results in an equation whose left side includes the accumulation of entity B inside the control volume, but also the net exiting flow of entity B through the control surface, while the right side is the variation of entity B in the system.
But what does this derivative of B system actually means?
Clever question. It can be interpreted as the corresponding value for the conservation principle written for constant mass. 0 if B is mass. Net force if B is linear moment. Net energy input if B is energy. But following Reynolds' paper description, it can be better interpreted as the appearance of B for other means that crossing the control surface accompanying the mass, or convective flow of B. In other words, the total mass does not appear inside the control volume, therefore the value of psi is 0 for mass. On the other hand, linear momentum is added to the control volume either by the action of mass forces, like gravity and centrifugal, or by the action of surface forces, like those associated to pressure and friction. Hence, psi is the sum of forces. Finally, energy is added to the control volume as heat flow or power that can enter or leave the control volume independent of the mass flow. Psi is then the net flow of Q and W. Summarizing, the Reynolds transport theorem allows an unified view of the three most relevant conservation principles in chemical and process engineering: the accumulation of B inside the control volume, plus the net exiting flow through the control surface, equals the appearance of B by other means than convective flow. For the conservation of mass, the accumulation of mass inside the control volume, plus the net exiting mass flow through the control surface, is 0. For the conservation of linear momentum, the accumulation of momentum inside the control volume, plus the net exiting momentum flow through the control surface, equals the net forces. For the conservation of energy, the accumulation of energy inside the control volume plus the net exiting energy flow through the control surface equals the net heat flow plus the net power. This was for now. On behalf of Professor Sorrentino, I want to thank you all for the attendance, and we would delighted to host you again for an additional episode of Process Fluid Dynamics. For more detailed explanations beyond the scope of this short video series, do not hesitate to reach Professor Sorrentino via email using the address josiasrentino@outlook.com. You can also visit the website sites.google.com. View Process Fluid Dynamics.